Alright guys, here we go with 16.1, and we might even be able to squeeze 16.2 in, but we'll see how it goes. Here's our first joke. It kind of goes along with our lab that we did Monday, today in class. I thought it was funny. Alright, we're going to go ahead and move on then. Alright, so hopefully by the end of this section, or the point that you have in your notes, follow these 16.1 properties that you see here on the slide. So first you need to be able to identify factors that determine the rates at which our solute dissolves. Second, identify units used to express solubility. And number 3 would be identify the factors that determine the mass of a solute that will dissolve with a specific mass of another solute. Okay, so here we go. Alright, solute formation. So we have the composition of a solution is the solvent and the solute. And how quickly that solute becomes part of the solution depends a lot on 3 main things. Agitation, so like when you stir it, you kind of move the particles, you aggravate it a bit, so that's agitation. Temperature is the second one, and surface area of the dissolving particle is the third one. All of these factors have to do with the solute and the solvent coming in contact with each other. Okay, so that's a good clue or indicator of how these things work. So below, you can see in the slide, I've added for you guys those 3 things and some points that help explain them. So with stirring, you have increased agitation, or the occurrence of new solvent being moved in towards the solute, and so those new solvent particles can grab more pieces from the surface of our solute. The second one is temperature. As temperature increases, kinetic energy also increases, and so this helps more collisions occur, and those collisions again take more parts of our solute away and become part of the solution. And then the third one is the surface area, or the particle size. So the greater the surface area is, or the smaller the particle size, the more surface area you actually have. And so now again, the solvent can surround the solute and pull atoms, particles away from our solute. And so that, all 3 of those, increase how quickly the solute dissolves into solution. Alright, so solubility now. Solubility, here are some terms we talked about in class. I think you guys understood these well, but I'll just go through them quickly, just in case. So solubility is talking about our solute becoming one with the solvent, kind of. And so it's expressed in grams of solute per 100 grams of solvent. Okay, so if I have 100 grams of water, how many grams of this solute, say salt or sugar, will dissolve in that 100 grams of water? If the maximum amount of the solute for a specific solvent is given, then we have a saturated compound. We can't put any more solute into our solution because it'll just stay in the crystal form. Okay, unsaturated means that we don't have enough of that solute yet. We can keep adding more solute and mixing it. Okay, and then miscible and immiscible, these deal with 2 liquids mixing together into a solution. So if they're miscible, they dissolve completely. You cannot see the difference between the 2 liquids. Immiscible would be like water and oil. You can see the two layers, and so you know they're immiscible. They don't dissolve into each other, okay? Even if you shake them up, they're going to separate, and you'll see those two layers. And so you can see that here in the picture I've got for you. Right here, you have the immiscible, because the particles are forming two layers. They don't mix well. Where on the other side, you have miscible solution or miscible liquid, and so the solvent and solute mix well together. Okay. And now factors that affect solubility. So temperature and pressure are the main two things that we're going to talk about with factors that affect solubility. Temperature will affect liquids, solids, gases, okay? The higher the temperature, usually the faster those substances will dissolve in the solvent. However, pressure also determines how a gas will dissolve in a liquid, okay? And so we'll get to that one last. All right, so again, this increased temperature is usually going to help things dissolve faster, but there are some exceptions that, like, I think it's yttrium sulfate will dissolve faster at lower temperatures and slower at higher temperatures. So there are some random ones like that. But the more common ones you would find in the table on page 475 of our textbook. I had to look for that. Supersaturated, we mentioned today in class, and I got a lot of confused stares. It's okay. Here it is. All right, supersaturated solutions occur when we have a saturated solution, but we cool it. And you would expect crystals to form because we've cooled it down, we've come down in temperature, but it actually doesn't form crystals. Okay, some might, but when a solution does not, that's a supersaturated solution. Blah. Say that 10 times fast. Anyways, it's theoretically not supposed to do that, but it does. It has more solute than it should at a given temperature. I hope that makes sense. If not, shoot me a message and I can try and reword that for you. Gases, however, are opposite from solids in regards to temperature. So usually gases are more soluble when the temperature is lower. Okay. An example of this is bodies of water. Okay, you have oxygen in water, especially lakes, ponds, rivers, which is good so that animals can live, and other organisms. They can capture that oxygen. However, when the temperature of the water increases, it causes the gases to be released. So there are not as many gas particles in our solution, in our water. And so that's bad news for those organisms as oxygen is released as temperatures increase. All right, and then pressure was the second thing. Changes in pressure really don't affect solids and liquids. They're mainly affecting gases. And so gas solubility increases as that partial pressure above the solution increases, like soda pop, whatever you want to call it. So when you open like a Coke and it fizzes, they have put a ton of pressure. And as you release that pressure, you also are releasing the solubility of the gas. The gases then can leave the liquid. And that is described by Henry's law, which you can see here. You've got S1 over P1, and then that equals S2 over P2. And so that's dealing with solubility of the gas and the pressure of the gas. And those you can find on 476. So let's do a problem. If you don't need this, then you can go ahead and move right away to this down here. Page 477, complete practice problem number 2. On the box, whichever side that shows up. Okay. If not, we're going to go through that practice problem together. So if the solubility of a gas in water is 0.77 grams per liter at 3.5 atmospheres of pressure, what would the solubility be at 1 atmosphere of pressure? Okay, so we keep temperature constant. It gives you the temperature. It's constant, so you don't have to worry about it. Okay, first we want to list our knowns and our unknowns. Okay, and you can see that I've done that. We want to find S2, the solubility, the secondary solubility, okay, when we change the pressure. And then we plug those into our formula, as you can see I've done for you down here. And your answer, drumroll, is 0.22 grams per liter. Okay, and so that is calculating solubility. And then your third thing would be to check, does it make sense? And it explains it for you on page 477. You can read, so I don't have to read that for you. And basically that is our 16.1. I think I'm going to have to create a second video to get 16.2 in. Even though it is shorter, it seems to have more problems in it. So I'm going to walk you through a few more problems and have you solve those for me. Okay. Again, any questions, any problems, email me. I'm awake till 10 p.m., maybe a little later, and I will get your emails probably around 6:30. Okay, so I'm free except within those windows. All right, see you guys.